Hello, differential equation students. In this video, we will see how to solve higher order linear differential equations. In this particular section, we are going to take a look at how to solve higher order linear differential equations with constant coefficients. And so which I call, higher order linear differential equations with constant coefficients. And we're going to take a look at how do we solve homogeneous case. So let's take a look at some examples. Here is the first order. As you see here is the first order because the highest derivative is the first derivative, and this is a linear differential equation, and the coefficients are all constants. It's 1 and 1, so we call this the first order linear differential equations with constant coefficients. Both are non-homogeneous. The homogeneous version for this would be if you want to say, it will be y prime plus y is equal to 0. Second one is also a first order linear differential equations with constant coefficients. Again, here it's 1, here it is 2. They're constant, so that's why it's a constant coefficient. And the corresponding homogeneous version of this would be y prime plus 2y is equal to 0. Third one is also a constant coefficients. As you see them, it's a first order linear differential equation with constant coefficients. And the corresponding homogeneous version would be 5y prime plus 2y is equal to 0. And here we have second order linear differential equations with constant coefficients. As you see here, y double prime plus 2y prime plus 5y is equal to ln of x. Again, the coefficients are all constants, 1, 2, and 5. And the homogeneous version of this would be, is going to be y double prime plus 2y prime plus 5y is equal to 0. Here is also the second order linear differential equation with constant coefficients. I'll let you complete the homogeneous version in here. Here you have a third order. As you see here you have a third order. And by the way, for those who don't know what this means, this is not the white cubed. This white, the y to the third, this means the third derivative, right? It's easy to write the third derivative using, these dashes, right? But if you say, it's okay to write it this way. But if you have a 2020th derivative, right? You're not going to have 2020 of those dashes, right? So for that reason, we say, this is y of 2020. That means that's a 20th derivative. Remember, this is different than y to the 2020. That means you're raising y to the, you're multiplying y by itself 20 times. This means you're finding the derivative of that function 20 times, right? So keep that in mind when you work with that. All right. Now let's see how do we solve these higher order linear differential equations with constant coefficients. So let's take a look at the first order, right? So if I ask you to find the solution to this very simple problem, y prime plus y is equal to 0. Again, this is a first order linear differential equations with constant coefficients. How do you solve that? You all know how to solve this. You can use the variable separable method. This is, same as saying dy over dx. As a matter of fact, we solved it before. Plus y is equal to 0. So if you do the variable separable, and you can rewrite it this. You can rewrite this one as minus y, and then if you simplify this, you're going to have negative 1 over y. Dy is equal to dx, and then you integrate with the negative dx, and you integrate. There's going to be ln of y is equal to negative x. And then you can see some sort of a plus c1, and then if you try to solve, you take the exponential on both sides, you're going to have y is equal to e to the negative x plus c1. If you simplify, you can say this is a constant times e to the negative x, where the c is equal to e to the c1, right? You know how to solve that. So the point that I want to say is the solution to this problem is, as we see, y is equal to e to the negative x times c. Now, if this was 2, let me ask you, what if this was 2? Y prime plus 2y. Then you do the same thing in here. You do the same thing in here. Then this is going to be negative 2, and that's going to be negative 2. So, and that's going to be negative 2, right? So, what I'm trying to say here is, suppose if the differential equation happens to be something like this: y prime plus 2y is equal to 0, then the solution happens to be y is equal to c times e to the negative 2x. And suppose if that happens to be 5, let's just say if this happens to be 5, then what happens, right? So if this was 5y, right, then you're going to have a negative 5y, then you're going to have, negative 5x in here, then this is going to be negative 5x, and you're going to be e to the negative 5x, this is going to be negative 5x, right? So therefore, what we are getting here is, if the differential equation is y prime plus 5y is equal to 0, then the solution to that one is y is equal to c times e to the negative 5x. And what if it was a constant k, right? What if this was a constant k? Then what's going to happen, right? If this was k, this would be k, and this would be, that would not be k, it would be minus ky. This will be minus k dx, and it's going to be minus k, it's going to be minus k, and it's going to be minus kx. So what I'm saying is, if I summarize what I have in there, as we see the pattern, right? As we see the pattern in here, right, in these problems, what we see is, we see that if the differential equation is y prime plus ky is equal to 0, then the solution is y is equal to c times e to the negative kx. So the question here is, now, is there a way we can represent this in a better way? Yes, right? And we are going to formalize it using something called characteristic equation. And what is that characteristic equation? Here is that characteristic equation. So what do? If you have a differential equation which is like something like this: y prime plus y is equal to 0, then the characteristic equation, right? Characteristic characteristic equation is this is how you do it. It's a y prime, right? And so therefore you're going to say m to the power 1 corresponding to this y prime, right? Let me write it down here below so you can see it even better. And then the second one is no derivative, zeroth derivative. So it's going to be m to the 0 equals 0. And if I simplify this, this is going to be m plus 1 equal to 0. And that's what we call that as a characteristic equation. So for example, so that's what we call that as the characteristic equation for that problem. So for example, if I have this y prime plus 20y equal to 0, the corresponding characteristic equation is going to be m is going to be m to the 1 plus 20 m to the 0, which is 1, equal to 0, right? And then m to the 1 is equal to m, so you can leave it like that. So in general, if you have, y prime plus ky equal to 0, the corresponding characteristic equation is going to be m plus k equal to 0. Now, let's take a look at the solution, right? Remember, this is a differential equation. The characteristic equation is a more of a linear equation in this particular case, right? It's like more of an algebraic equation. M is like a number, right? M is not the derivative. We wrote the characteristic equation from the differential equation where the power of the M corresponds to the derivatives of the Y. Now let's try to solve these, right? So if we solve this first characteristic equation, my solution is M is equal to -1. If we solve this one, this is going to be M is equal to -2020. If you solve this one, this is going to give me M is equal to -k. And if you look at the solution to this one, and if you take a look at the solution to this one, the solution happens to be, as you see here, y is equal to c times e to the -x. And the solution for this one is y is equal to c times e to the -kx, right? So basically what you have is, when you have this first order linear differential equation, something like this, right? When you do the characteristic equation, and then you solve for m, and then the power, right? The coefficient of the power of the x, right? The coefficient of the power of the e, right? The coefficient of the x in the power of e is actually that right there. So in general, if the root or if the solution, if the root is m, right? Then the solution is y is equal to c e to the mx, right? So that's a very important thing that I would like you to remember. So now let's try to summarize what I'm saying right now. So if we have to write it as a summary, what I'm saying is the following. If the differential equation is given to you, something like a constant times y prime plus another constant is equal to 0. Step 1, write it in the characteristic equation form. So I'm going to say CHEQN, by which I mean characteristic equation, which is A times M plus B is equal to 0. Then step 2, solve for M. In this case, if we solve for M, it's going to be M is equal to minus B over A. The step 3, your solution is going to be C times e to the mx. In this case, that will be y is equal to c times e to the negative b over ax, right? And that's how we solve first order linear differential equation. The question is it possible that we can extend this to second order linear differential equations? The answer is yes, we can do that. So let me show you how do I do that. Again, the idea is very simple, just like we did earlier. So let's see what do I mean by that. Let's take a look at this differential equation. The differential equation that I have is, let's just say y double prime minus 2y prime minus 8y is equal to 0. Let's see, let me try to figure out the characteristic equation. The characteristic equation, which is in this case is going to be a quadratic equation because y double prime corresponds to m squared, minus 2 times y prime corresponds to m, minus 8 times y0, the derivative corresponds to m to the 0, which is equal to 1. So I can just leave it there. So that's all I have. So the next question is, now I can find the root of this, right? Because it's a quadratic equation. You all know how to find the roots of this particular equation. So let's see if we can do that. So again, we know how to do that. We're going to factor it out. If I factor it out, you agree this is going to be m minus 4 times m plus 2 equals 0. And that tells me m is equal to 4 comma minus 2. So the question is, so what is the solution, right? The solution is simple. And that solution is going to be, we're going to say y is equal to, remember it's a second order, right? So we're going to have 2 parameter family of solutions. So we're going to say the solution would be c1 e to the positive 4x plus c2 e to the negative 2x. As simple as that. So, but before I do that, I want to, as a practice, because we're going to need this later, as a practice, what I'm going to write down is, so because of the 4, we're going to have an equation, we're going to have a solution that's going to be e to the 4x. And because of this negative 2, we are going to have a function that is e to the negative x is going to be part of the solutions, right? So I want to put them in the set notation, right? And I'm going to call them, this is f dot s. What do I mean by that? I'll let you know later. But as a practice, I'm going to write it down as the fs. Let me just tell you what do I mean by this. Then, this is called a fundamental solution. These are called fundamental solutions. We'll talk about it later. But as a procedure, I want you to write down as soon as you have this, as soon as you have these roots, write down the corresponding fundamental solutions. And this is called a linear combination. Again, we'll talk about it more. This is called a linear combination of this set, right? That's a set notation. So your solution is going to be, something as a constant times another constant. Maybe 2 times this and 4 times that, or 5 times this and 3 times that. It depends on your initial condition, but the solution is, no matter what the no matter what the initial condition is, the solution is always going to be something to the e to the 4x plus something to do with the e to the negative 2x, and though something is going to be a constant multiple of this plus another constant multiple of that. So that's how we would solve this. Let's take a look at another example and see how do we solve that. Let's see. Let's take a look at this differential equation. Differential equation that we have is, let's just say, y double prime plus 4y prime is equal to 0. Then the step 1, I'm going to say, the step 1 is write down the characteristic equation. The characteristic equation is m squared plus 4 times m is equal to 0. And I'm going to solve for m. When I do that, it's going to be m times m plus 4 equal to 0. And that tells me m is equal to 0 comma minus 4. And therefore, as a practice, I'm going to say the fundamental solution set, right? The fundamental solution set is going to be e to the 0x and e to the negative 4x, right? And if I rewrite it, that will be e to the 0 is 1 and e to the negative 4x. And so therefore, the solution is y is equal to a constant times 1 plus another constant times e to the negative 4x. And again, these are second order linear differential equations, as we said in the previous chapter, which means we are going to have 2-parameter family of solution, and we do have 2-parameter family of solution in here. Here is the one, here is the another one. And that's how we will solve it. So let's try to summarize the process. And by the way, this process works not only for this one, even for a third order, fourth order, fifth order, anything that we have. We'll take a look at this. Let me try to summarize the steps. So the step 1 in solving homogeneous one, the step 1 is you're going to be given a differential equation. The step 1 is to convert this into a characteristic equation, right? That's your step 1. Step 2 is to solve that characteristic equation. I'm going to say solve for m. Some book uses r. That's completely okay. There is nothing wrong with that. I think you're going to see books using r's, even other notations. That's okay as well. And the step 3 is going to be writing down your fundamental solution set, which is going to be, e to the, let's just say, in this case, if you have 2, let's just say m is equal to m1 comma m2, then you're going to have e to the m1x and e to the m2x. And the step 3 is write down the linear combination as a solution. So the solution is going to be y is equal to a constant times e to the m1x plus another constant times e to the m2x, right? And that's how we do that. Again, this is not only for the second order. If it's a third order, the only difference is you're going to have m3, and then you're going to have, e to the m 3x. And if it's a fourth order, you're going to have m4, then you're going to have e to the m4x. And then in general, if it's the nth order, you're going to have mn, and then you're going to have e to the mnx. And then your solution is going to be plus c3 e to the m3x dot cn e to the mnx. And that's how you solve higher order linear differential equations with constant coefficients that are homogeneous. Again, this only is applicable to homogeneous. Non-homogeneous cases a little bit different. That's how we would solve them, right? So now let's take a look at a couple of these things, right? So when the roots are very simple like this, right? When the roots are very simple like this, then it's okay. You know how to solve them. But if I give you a problem like this, remember it's a second order, right? Let's just say let's just say I have this one. Let's take a look at this differential equation, which is as simple as this: y double prime minus 2y prime plus y is equal to 0. Whose, if you follow our process, the characteristic equation is m squared minus 2m plus 1 equal to 0. And then the solution is going to be, m minus 1 squared equal to 0. That's the factor. And m is equal to 1, 1. So therefore, your fundamental set is going to be e to the 1x. And the solution is going to be constant times e to the x. Is this correct? Remember, it's a second order linear differential equations. That means this is going to have two parameter family of solutions, but I don't have that. I only have only one. So then what's going to happen is something else is going to happen. So when you have a repeating roots, right? When you have repeating roots, something else is going to happen. And what is going to happen is it's not going to be this. It's going to be a little bit different, and that is going to be this. So you're going to have, when you have a repeating root, since this is repeating, you're going to have x times e to the x as part of your fundamental solution set. And so therefore your solution would be c1 e to the x plus c2 times x e to the x, right? And so there are things that are going to be changed. Again, now what if you have complex roots, right? Then how do you work with the complex roots and so on? So let me give you an example of a complex root problem. Let's take a look at this. Let's just say the differential equation is y double prime. Let's take a look at as simple as that. Plus y equal to 0, right? Then what happens? Well, then the step one, right, is our characteristic equation, which is, by the way, in this case would be m squared plus m equal to 0. Is that right? And that's not right. Actually, I goofed up, purposely goofed up. This should be m squared plus 1 equal to 0. Some of you are going to be get confused and say m squared, plus m equal to 0. That's not right. So it's going to be m squared plus 1 equal to 0. And therefore, your solution is m squared is equal to negative 1. So therefore, m is equal to plus or minus 1. Is that right? I'll give you 3 seconds. That's not right either. This is wrong. It should be m is equal to, remember, m squared cannot be negative, right? A square of a real number cannot be negative, so we have to use the complex root. So m is going to be plus or minus I. In that case, then how do we solve that? Well, now then therefore you're going to say, well, the fundamental set is going to be, if you simply follow my steps, e to the ix and e to the negative ix. And so therefore the solution is, you're going to say y is equal to c1 e to the ix plus c2 e to the negative ix. Is that wrong? No, that's not wrong. That's all right, but that's not how you write down the solution, because then solving this is not easy, right? So how do we write it? If you remember the Euler's identity, right? Euler's identity, and by the way, which is considered to be the top 5 inventions, right? That's along with the penicillin, exponential function, pi, and so on. So anyway, so if you remember the Euler's identity, which is e to the the Euler's identity, Euler's identity, e to the I theta is equal to cosine theta plus I sine theta. And but if you remember your pre-calculus, right? You've done things like this, and you worked with things like this in your pre-calculus, and you would have learned that e to the ix is equal to cosine x plus I sine x. And by the way, the Euler's identity is write down the Euler's identity, which is, by the way, e to the I pi plus 1 equals 0. And by the way, this is highly, it requires, highest level of intelligence to do that. If you really look at this, let me quickly show something here. If you take a look at this, you have an exponential function, and that's not even, you have a e, right? That's actually if you take a look, that's actually irrational number, and you're raising it to the power of a pi, it's also an irrational number, and then I is multiplied, which is a complex number, and you're raising to the power of the e. I don't know how do you compute that. And he comes up and says that must be equal to -1. This entire quantity must be equal to -1. That's, it's not like, approximately or like close enough or something. He says exactly, precisely -1. That's I think is only Euler can do it. Anyway, so using this, we can rewrite this. There are nice books, take a look at, you have internet too, take a look at the beauty of this Euler's identity. Anyway, we can use this and say the solution to that would be y is equal to cos C1 cosine x plus C2 sine x, right? So we're not going to write it this way. Going back to what I was saying earlier, we're going to write it this way. Rather, we are going to write it as, we're not going to write it that way. We're going to say the fundamental set of solutions, or fundamental solution set, is going to be cosine x and sine x, and therefore the solution that we write not this way, rather this way. All right, so let's summarize what I just said, right? Let me summarize what I just said. So when you have a second order linear differential equations, you're going to have three cases. The case number one is the roots are real and distinct, that m1 is not equal to m2. The case two is the roots are real and same. Roots are real and the same, or in other words, it's repeating. And the third case is roots are complex, right? So something like that. Now, how do you do that? When the roots are, and so let me talk about the fundamental solution set. When the roots are real and distinct, what is going to happen is that you're going to have m, as we see here, is equal to m1 and m2. In this case, m1 is not equal to m2. So therefore, the fundamental solution set is going to be e to the m1x and e to the m2x, right? And that's it, as simple as that. And so therefore, the solution for this would be y is equal to c1 e to the m1x plus c2 e to the m2x, as simple as that. If you take a look at the case 2, where the roots are repeating, right? Where the roots are repeating, then what do you do? Well, then your fundamental set, as you see here, since it's repeating, your root m1 is equal to m2, and let's call both are m, right? Then your fundamental set is going to be e to the mx times x e to the mx, right? And so therefore the solution would be y is equal to c1 e to the mx plus c2 x e to the mx. Now, what do you have when the roots are complex, right? What do you have when the roots are complex? When the roots are complex, what's going to happen is that you're going to see, let's just say m is equal to alpha plus or minus I beta. You have a real component and you have an imaginary component, right? Then the solution set, the fundamental solution set is going to be e to the alpha x times cosine beta x, e to the alpha x times sine beta x. And so therefore, the solution would be y is equal to c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x, right? Now the question is, how do you solve the higher order linear differential equations with constant coefficient? And by the way, these are the three cases that we're going to work. These are the three cases that we're going to have. Now the question is, what happens if it's when you're dealing with multiple, right? What happens when you're dealing with multiple in here, right? Something like this. What happens in here if you have many of them in there? So here I assume that every one of them, they're all distinct, right? Here I assume them, right? Each and every one of them are distinct. Then you have this a fundamental solution set, right? And then you have the solution like this, right? But what if it's not all of them are repeating? What if you have some of them repeating, some of them complex, some of them distinct? Then how do you work with that? It's the same process. It's the exact same process. Let me do one problem and then we'll see how this works. So let's take a look at this one, the third order one. The third derivative minus 4 times the second derivative plus 3 times the first derivative equal to 0. Let's see how do we solve this. The idea is very simple, just like we had earlier, right? And we're going to mix these three. That's all. What we are going to do is we're going to mix these three cases, and that's how we're going to solve. So let's take a look at how do we do that. The steps are very simple, as we said earlier. The first one step is to write down the characteristic equation. If I write down the characteristic equation, ladies and gentlemen, I am going to have m cubed minus 4m squared plus 3m equal to 0. And if I factor this out, I can take the m out, then I will have m squared minus 4m plus 3 equal to 0. If I further factor this out, this is going to be m minus 1 times the m minus 3 equal to 0. That tells me m is equal to 0, 1, 3. Well, this is simple. Therefore, fundamental solution set is going to be e to the 0x and e to the 1x and e to the 3x. And hence the solution is, y is equal to, by the way, this is 1, right? So c1 times 1 plus c2 times e to the x plus c3 times e to 3x, right? That's how you solve it. Now, now let's take a look at how do you solve. Let me give you another problem in here. Let's take a look at this problem. For the differential equation is fourth derivative plus 6 times the third derivative plus 5 times the second derivative minus 24 times the first derivative and minus 36 times y equals 0. Then the corresponding characteristic equation is, as you see, would be m to the 4 plus 6m cubed plus 5m squared minus 24m minus 36y equal to 0. 36 not y equal. Is that right? That's not right. That's not 36y equal to 0. It should be simply 36. Now, again, you can use something called synthetic division to solve it. I'll let you solve it on your own. If you solve it, you're going to have the roots are going to be the following. right? So remember, this is our step 1. I'm going to do the step 2, the roots. The roots are going to be 2, -2, and -3, and -3. Now you see here, you have 3 distinct roots, 2, -2, -3, but -3 is repeating, right? So how do you find the fundamental solution set? The way that you do is, you're going to say fundamental solution set in this case is e to the 2x, because there's only one of them, e to the -2x, because there's only one of them, and e to the -3x, that's correspond to the first 3. That corresponds to the, the first 3, right? And then what about for this one? For that one, the fundamental solution is going to be x times e to the -3x. And so therefore the solution is y is equal to c1 e to the 2x plus c2 e to the -2x plus c3 e to the -3x plus c4 x e to the -3x. So that's how you would solve that, right? Now that's a solution to that problem. That's how we solve, higher order linear differential equations with constant coefficients. So let me quickly show you a few other things, and then, we will move on to the next video for solving non-homogeneous case. Let's take a look at this one. Suppose if the roots are, I'm just making this up, right? 0, 0, 1, 2, 3, 3, 4, and 5, 5, 5, 5. Then I have, let's just say, plus or minus I, and 2 plus or minus 3i. Then how do you do that? Well, the corresponding fundamental set of solution is going to be, this 0 corresponds to 1, and this 0 corresponds to x times 1, and this 1 corresponds to e to the x, this 2 corresponds to e to the 2x, and this 3 corresponds to e to the 3x, and this 3 corresponds to x e to the 3x, and this 4 will give you e to the 4x, and this 5 will give you e to the 5x, and the second 5 is going to give you x e to the 5x, and the third 5 is going to give you x squared e to the 5x, and the fourth one is going to give you x cubed e to the 5x, and the first I, and the I plus or minus I, remember they always, complex, the roots occurs always in pairs. So that I corresponds to, let me do a different color in here so you can see it. That I corresponds to cosine x and sine x, and 2 plus or minus 3, let me do a different color. 2 plus or minus 3 would correspond to e to the 2x cosine 3x and e to the 2x sine 3x. And by the way, you can write it in any order. What do I mean by any order? You can write the cosine first and then the cosine later, but that's how it's going to be. All right, let me give you another example. What if you have something like this? M is equal to, let's just say, 1 plus or minus 2i and 1 plus or minus 2i. Complex roots are repeating now, right? So what would be the fundamental solution set? The fundamental solution set for this would be e to the x cosine 2x, e to the x sine 2x. That corresponds to this one, right? Now what about for this? For that, what you're going to have is for this, what you're going to have is the following: x e to the x cosine 2x, x e to the x sine 2x. It's multiplied, right? It's multiplied. So let me rewrite it just in case. So you can apply this, repeatedly, and then get solutions to any problems that has the roots, right? So that's how you would solve, higher order linear differential equations with constant coefficients that are non-homogeneous. In the next section, we'll take a look at try this problem. The next section, and by the way, here I've given you an initial condition, right? Make sure to use this initial condition to figure out those constants. In the next chapter, next section, in the next video, we'll take a look at how to solve the higher order linear differential equation with constant coefficients that are non-homogeneous, right? So how do you do that? We'll do it in the next video. We'll stop it right here.